Okay, so that's one of the things that we will do. And hopefully we'll have time. We will also look at this concept of fractals a little bit and how you can draw some very interesting fractals and the basics of what is the maths behind it. Okay. Okay, one reason for these choices is R is completely free software. And also there are many websites where you can just type in R and the results will pop out. So you don't even need to necessarily install it on your computer. So that's very convenient for today. And Mathematica is a paid software, but that also has a sort of restricted but free version that is available online. So that is, I mean, it's good enough for most basic things. It has some restrictions on how complicated, other computations you can carry out, how much time they can take. But those are pretty generous restrictions, so they don't really affect, and they won't affect what I want to do. Okay, so let's try this. Try and open this website. And in fact, if you just type something like art online, this should be one of the first couple of links that come up, and you could just click on that. Yeah, program is the first one, right? Okay. So just type art online in the search, and this programming website seems to be the first one. You can see that I was also lazy. I didn't go searching for better one. It seems to do what I need personally. Okay. So if you have opened it, have you managed to find it and open it? Okay. All right. Let me point to something here. Wherever there is this hash and there is some text, that means that is there's some comments. So we can just, that's not something you need to type. It's some explanatory sentence there. And when I show you commands later, whatever is after a hash, just read it and ignore it. Don't waste time writing it. Okay. But the other stuff, like that message and print message, those are commands to try. What you could do is this is just, if you open it, that's the first thing you see. Just click on run, see what happens. Code execution successful. Successful, but something else should have happened. And this message is displayed. The message was also displayed, right? Try programmist.pro also was displayed, right? So that's pretty easy to see what happened. In that line 4, you have created that message. I mean, you have created something. Message is a name you gave. You could have called it something else, doesn't matter. So you chose a name message, and that arrow is okay. Whatever is after that is being given that name. And so now, from now on, message stands for that phrase. Try programmist.pro. Okay. And then you just say print it so students it can have. Okay, so that's one of the nice things about R. It, on the whole, it's very straightforward, and the commands are very sort of intuitive and easy to understand. There's no complicated syntax as such to worry about. Okay. I mean, you do need to learn some things, but not that much. Okay. All right. Let's not look at it right now. Now the question is, suppose I want to talk about probability in the class. Okay? Now, in high school or college, they have already heard this word and they have some idea about it. Okay, so what do you think if I ask a student, what do I mean if I say probability of getting hits when I toss the coin is half? What is likely to be the response? Like, why do we say it is half? Yeah. That is the most likely thing that they will say. That it could have been head, it could have been tail, so each became half. Each became half. Okay. Then, I mean, this calls for some discussion. You have to ask, okay, so is it always the case that if I have just two options, then they will have probability half and half? Could be different. You can think of some situations. For instance, What's the probability this fan falls down in the next 5 minutes? Okay.
0.00.
Cool, yeah. But you probably would say half. Hopefully,
Is equivalent.
hopefully it is not half. Yeah. Okay. All right. So then you have to ask, okay, it's not that. It's not just number of cases and you divide by that. Right? What else could it be? What if I say it is half, what am I trying to convey?
Equal likely.
Okay, but again, like equally likely just means there were two things, half and half. So that's just the name for saying that I said half and half.
Bias.
We are talking about random experiments.
Right. So like in simple language, what would one say?
Alpha is if I do n number of tries, then I'll get
Uh,
10 by 2 times.
right. So this is a prediction of what will happen if you toss the coin many times. You're saying that if you toss it many times, then you expect that about half the time it will show heads. Half the time it will show heads. And then we tell the student that yeah, if you toss it 10, it will not be 5 and 5. It might be 6 and 4, it might be 7 and 3. But if you do it 100 times, it won't be such a gap. If you do it a million times, it'll be really close.
Maybe it depends upon the number of options you have for it.
But let's stick with the coin.
Chances.
Yeah, but let's stick with the coin because in that simple thing itself, we have to see if we understand. Now we say all this in class, but why should the student believe us? If I toss it 100 times, it is as likely that I'll get 40 and so on. Now, the one way out is to actually take a coin and start tossing. Some years ago, I came across a person in the US. He got two undergraduate students to actually spend time every evening tossing a coin. That was his, they were his assistants. And they ended up tossing it some 20,000 times. And then there are nice things, but we can't do that every day, right? We want something else. So one thing is we can ask the computer to do this for us. All right. What that means is the computer needs to be able to look at some list and pick one in some way that appears random. It can't really be random, but it should mimic randomness somehow. We won't get into how it does that. Let's take it for granted that it has some means of appearing to randomly select one out of many things. And then you can ask it, if it can do it once, you can ask it to do it repeatedly. Okay, so in R, here is one way to do it. So don't read the whole thing. Now, first I need to create a situation where I'm picking from two things. So I'm choosing for this the number 0 and 1. This is an arbitrary choice. Could have selected some other numbers or even the letters, etc. Okay. But if you choose numbers, then it makes counting easier later on. So I've chosen the numbers 0 and 1, and I'm going to ask the computer to randomly select from one of them. And then I'm going to ask it to do that many times. Okay. So that is the first line of code. Sample means, okay, pick one at random. Where do I pick it from? 0 colon 1 means all the numbers, all the whole numbers from 0 to 1. That just means 0 and 1. But suppose I wanted to mimic tossing a die, then I would want it to go from 1 to 6, which we'll look at later. So that's the first part. 0 to 1 is saying choose from 0 and 1. That's okay. The next one is saying how many times. So that is 10. Okay. And the next is if you choose, just imagine this was something physical. There were two things and I pick one. Now, how do I pick again?
The lights where it's visible.
Okay. Yeah,
Can you try? Actually, madam,
These two, I think.
oh, perfect. I think the glow must be from there, not from the one behind.
Yeah.
दोनों ही है
ये दोनों की reflection है.
Actually, both probably.
वो on कर दो.
That's okay. Maybe that. How bad is it?
It's not better.
Okay. Okay, so now, so when you pick, and then you want to pick again, the question is, what did you do with the first thing that you picked? Did you put it back or not? So that is whether you're picking with replacement or without. So we have to tell it which one it is. Okay. So replace equal to means every time you pick, put it back. If I didn't want to put it back, I wanted to pick something else, then it would be false. Okay. Okay. Or I just type that line 2 into your R thing and then press run and see what. So type sample, brackets open 0, colon 1, and then comma, and then 10.
Execution successful and it's giving me some
It's giving you some number, right? How many numbers?
1 0 1 1 0 1 1. So 6 7 1 3 0.
Yeah, so it's done in 10 times. Forget all the other numbers because it's running all these lines. Just concentrate on the. Okay, you only did one line, so you will only see that first row. But hopefully you are seeing different sequence of 1 and 0. Hopefully, okay, some might see the same one, but others hopefully are seeing various different sequences of 1 and 0. Is that happening?
Yes.
Okay. So what has just happened is that it has actually picked 10 times from 1 and 0. On my screen, the first time it picked 1, and then 3 times it picked 0, and then it picked 0, 1, and then 0. Is that okay? Happening?
Yeah.
नहीं तो अभी तो वो नहीं खोल सकते हैं वो लाइन नंबर दिया होता है
Sample
This
0.
you don't need. This was इसको आप छोड़ ये पुराना भी उठा सकते हैं आप ये नहीं क्लियर से आउटपुट उसको मत दीजिए
User we have to type from the very first line.
No, ignore the, remember what I said, whatever is after hash, ignore that. That is a comment, you don't need it. You want to actually run it. Only type line 2, the one starting with the word sample.
Nothing is coming out. Run kiya?
Run. So type that line, sample, etc. Only that line, and then click on run. Yeah, hopefully you will get different output because each time is that. Because you did not miss.
10 में देख सकते हैं.
Zero colon 1, right? And then a comma, then a comma, then replace equal. That doesn't really matter, but good. और उसके पहले कुछ नंबर आ रहे होंगे कितने नंबर आए 10 आए ना 1 2 0 10 1 so that's what is done, right? 10 times it has picked. Sometimes it has picked 1, sometimes it has picked 0. Just click on run again and see if your output changes. Just click on run again. If it's random, then you should get something else.
Yes.
Yes, yeah. Okay, that's the random part, right? Each time you get a different result. So there's like getting the computer to toss a coin for you 10 times.
We don't try.
I don't want to just toss it 10 times. I want to toss it thousands of times so that I can see what happens in the long run.
I did 151 and 40. 10 by 1000. Just
No,
replace
don't
10.
do it just now. Not only
Is it optional? Can we replace? Remove this not replace.
no, don't remove it. This is very important. Without it, it will fall apart.
यहाँ पे गलती है देखिए.
Yes, sir, I have made 20 times.
Okay, great job.
Got this, sir.
Unexpected semi. Oh, ये semicolon है.
कहाँ से आ गया? सब कोई नहीं. Like 7th. Oh, I see. Just tells you how many.
So I think you have
They will call it some. Some and that will call it some.
yeah. Okay, इसको क्या चुका? This is what. I think you say silence के लिए सिर्फ message हटा दो. You can say print करके. Yeah. Okay. You could try changing that number 10, like change it to 620, 30, whatever you like. कितना करेंगे हो जाएगा. ठीक है. पर ज़्यादा करेंगे तो इसको.
Execution order.
Because the lines are
The power
so that's what 1,000. Okay. It might be running 6 of space.
1,000.
But I think it will take more space. You can't really literally absorb what is happening when the 1,000 rounds going. Right? So once the output is very large, okay, hang on. I can't talk. You need to quiet down a little.
Everybody, please pay attention.
And people are paying attention, but and they're being asked to pay attention to three things at the same time. Okay. All right. So now I want to generate 1,000,000. I want to do 1,000,000 coin tosses. Clearly, I don't want it appearing on the screen. Okay. So what you do is you direct where you want it to go. I'm going to create, like we earlier created the name message, I'm creating a name coin. And then, this arrow, the less sign and the dash, and then my command for generating 1,000 outputs. Sample 0 to 1, 10 to the 6, replace equal to. Okay. So what does this do? This does all the computation, but the answer is stored in an internal list that it creates called coin. You don't get to see it. You can print it if you want to see it, but right now it will just stay there. And now I want to explore what is in that list. Right? How many heads do I have? How many tails do I have? How many heads do I have in the first 100 tosses? Okay, we can start exploring that. So now, okay, just do line 4, okay, because we need it to go further. Don't ignore all the hashed lines, okay? Just do line 4, coin, and then the arrow pointing to coin, and then sample command. Okay. And then run. Okay, then run it. It should show you it's successful. It shouldn't show you any numbers because you put it in coins, not for display. Okay. Able to do that?
सर एक बात, जो रिजल्ट आउट आई ना 1001 उसका मीनिंग क्या हुआ? ट्रू किसको लिखा है?
नहीं ट्रू ना 0 है ना 1. ट्रू ये कि जब भी जो भी उठाया उसे वापस रख दिया ताकि फिर से दिक्कत. अगर 1 किया तो फिर वापस रख दिया ताकि नेक्स्ट टाइम फिर से ऐसे ना हो. Right, because you still have this print message. Because that also not
ये तो रेशियो
ये रेशियो नहीं है, ये 0 to 1 रेशियो है, ये दो नंबर है, जिनमें से आप पिक कर रहे हो।
अच्छा क्यों 0 1
0 और 1 में से आप पिक कर रहे हो, तो कभी आपने पहले 0 पिक किया, फिर 0 10 बार किया। हाँ, but I want to count. Okay. All right. तो ना आपने कॉइन में सेव करो ना, आप उसको प्रिंट करो।
कॉइन में क्या है?
और उसके पहले क्या है?
उससे पहले वो तो चल गया ना, चला गया। आपने फोन से इसको क्या दिखाया?
So okay, just you could go with a smaller number in that. You 10 to the 6 or 10 to the 4 continue. You can put the other type plus that may be the intent of the thing. एक तो वो जो पहले सैंपल था उसको हैश कर दीजिए ताकि वो बार बार 0 1 में कॉलम ही है, इसमें 6 कॉलम्स होते हैं।
Oh, yes, yes.
नहीं उस पर मैजिक नहीं है, वो बस आपको दो ब्रैकेट दिखा रहा है, हाईलाइटिंग। वो अभी मैं पहुंचेंगे नहीं हूँ, पहुंचूंगा तो पता, आगे मत जाओ।
Sir, code execution successful. Okay.
Avi, nothing will show. Okay, what has happened is internally 1 million processes have happened. Data is stored in coin. Nothing is shown. How we will change. Okay. Okay. So if you have done line 4, now I want to see how many zeros there were. Suppose 0 stood for tail. So I want to see I tossed it 1 million times. How many zeros did I get? Okay. So there is the sum command. What you do is you take the list you have created. Double equal means it's a test. Coin equal equal 0 will look at each entry in that list and ask is it equal to 0 or not. Okay, and applying sum to the thing means what is the total number of yes answers. How many entries were actually equal to 0. Okay. Okay, but just type it and run it also. Okay. If line 4 has worked, then try line 7. Okay. Sum coin equal 0. For instance, answer coming out of 7 was 499912. Right? That's how many zeros there were in the list. And you should get some other number based on whatever happened.
This is the number of 40.
No, coin equal 0 will be the number of zeros. Right? I'm asking sum means how many times did something happen? How many times did I see 0? No, forget that. Initial one has no meaning in the output. Just ignore it. Just look at this number in your row. Like I got 499912. You should have some number here 500,000. Okay, good. Okay, 4995 ऐसे कुछ आना चाहिए. It should be around half, right? Alright, so it's like total number of zeros out of 1 million. Now I actually want to know the fraction. You could of course divide this by a million. But then if you change the number of coin tosses, you would have to manually change. Okay. So instead you can ask for mean. Okay. replace sum by mean. Mean coin equals 0 will give you the fraction of times that 0 was seen. Okay. So that is then 0.499.
Nine six two seven.
मतलब 500,000 के पास है ना, that's what we have ideally happened. Okay. Now suppose I want to explore, like, what was happening over time, right? How many zeros did I have? What fraction did I have in the first 1,000? What fraction did I have in the first 100,000? And see how that ratio changes as I toss more and more. Then I can just look at a part of the list and only in that ask what is the fraction of zero. So then the mean command is slightly changed. Mean coin, now in square brackets 1 colon 100. This is asking in the first 100 entries how many zeros were there, what fraction was there because of this mean command. Right, okay? Okay, so if you just apply it to coin, you are applying it to the whole list, but you can say which ones you really want. So for instance, if I'm curious about what happened in the first 100 tosses, then I apply main command to coin and then in square brackets 1 colon 100, right? All the entries from 1 to 100. And for instance, for me, that fraction turned out to be 0.54. So in the first 100 tosses, it wasn't that close to 0.5, but by the time you reached a million tosses, it was very close to 0.5. Right? So you can sort of see the kind of phenomena you want to describe to students. You can see it actually happening in this simulation. Okay. And for instance, how much was it in the first 10,000? When you do the same command, but with 10,000 instead of 100, that was 0.4984. You can see sort of the convergence. 0.54 when it's only 100 tosses, 0.498. When it's 10,000, 0.4999. Okay, when it's a million, getting close to 0.5. So you can see the settling down that you want to convince students that, okay, take more and more and it will proportion will approach up. Right? So that's experimental evidence you can show them for what is happening. Okay.
तो जो मीन का मतलब हुआ इधर ना, जो मैं समझ रहा हूँ, मतलब एक बंदे ने किया 1000 बार, किसी और ने किया 1000 बार, किसी थर्ड ने किया 1000 बार, उनका मीन का
नहीं,
जो उनकी प्रोबेबिलिटी आई,
प्रोबेबिलिटी कोई कंप्यूट ही नहीं कर रहे, हम तो बस काउंट कर रहे हैं. हमने 1000 बार टॉस किया, ठीक है. और क्योंकि 0 और 1 ले रहे ना, तो मेन निकालने से वो फ्रैक्शन ही आएगा. What is mean, right? You will add all the zeros and all the ones and divide by the total number. Right?
वो तो एक वोट वन आएगा.
हाँ, तो इसमें जब वो जो मेन इसमें क्या हो रहा है कि जहाँ की बेसिकली वेरिएबल जो कॉइन 0 is true ना, इसको इन these things that counts as, उसको उसने काउंट कर लिया एक. तो अगर 550 बार उसको एक मिले तो उसने 550 एक जगह रख दिया. फिर उसने देखा टोटल कितना था, उससे डिवाइड कर दिया. So that gives the fraction के 0 कितने में आ रहा है. So it will mean in that way. Okay. Now this is a way to kind of methodically do what we did in the last slide. In the sense, if I want to show someone, okay, after 1,000 tosses, 2,000 tosses, 3,000 tosses, what was the situation each time? Instead of manually doing it 5-10 times, I can do it, by just telling it to just release it. Okay. All right, this time I've just taken 1,000 tosses, right? Coin and sample 0 to 1,000 times, replace equal to, it's all stored in coin. Okay. Now see this one, right? Just the C1 is to 10 cube. Okay, C is for create. It just creates those numbers, makes a list of those numbers. So this makes a list 1, 2, 3, 4, 5, okay, 1000. Okay, there's nothing random in this one. Okay, so the second line, C 1 is to 10, 1 is to 1000, just creates a list of numbers are in sequence 1, 2, 3, up to 1000. That basically allows me to track it. Okay, where is 400, where is 500. All right.
So the C in front of the brackets is the
Is to
count.
create this list whose members are 1 to 1000. Okay. Now what do I want? If I have say 1000 tosses, I want to see the first 100. What was the fraction? First 200. What was the fraction? So till any number, if you want to see what was the fraction of the there's a cumulative sum command. I mean, what was the total until there? There's a cumulative sum command. CUM. Okay. All right. So I do this and take the coin and divide by toss. Okay, now what happens is there are two lists. So what do I mean divide one list by another list? What could it mean? So suppose there's a list of 10 numbers and there's another list of 10 numbers. And I say divide the first list by the second list.
Same.
It means divide the corresponding entries. Divide the first entry of one by the first entry of the second. Okay, okay, blackboard would have carried this over there. Okay, let's see. Maybe I can type something on on a blank slide. No, no, but that won't let me show them. Okay, so let me just show you in small, I mean, in a small example, what's going on here, right? Let's say these were the results of tossing a coin 5 times. Then, so that's in my coin list. Then I'm creating another list that just helps me locate things. It just has numbers 1, 2, 3, 4, 5. Okay. That was the list called toss, which I had created on the previous slide. Okay. All right. Then you take the first list, the coin list, and you apply the cumulative sum. So what does that do? It just adds up all the entries up to the particular entry. So for instance, I add the first entry. I just take the first entry. So I get 1. Okay. That becomes the first number of my new list. Then I take the first 2 entries and I add them. Right? I still get 1. That becomes the next number. I take the first 3 entries and I add them. Right? So now I've got 2. Okay. And then of course it stays at 2 because I don't have any other. Okay. Now if I take this list and divide by this list, what will I really be counting? Okay. So what will happen if I divide divide the first list by the third list? What will be my first entry? 1. Okay. Oh, sorry, not the first. I misspoke. Yeah, this by this, right? So I'm trying to see until a certain location, how many ones had I seen? Right? Okay, this is 1 by 1, right? That's fine. Next time it will be 1 by 2. That will be the fraction that were 1, right? Half of them were 1. Okay. right? Next time, 2 by 3, and that's the fraction, right? 2 out of 3 were 1. Okay. So this way I can count until any stage what fraction have been 1s. Okay. Is that okay? That's making sense?
Yes.
Now, right, this is manual. We are just writing commands to do exactly this. Okay. So this was creating those cumulative sums, and here I was dividing by 1, 2, 3 to get the actual fractions. Now that will create 1,000 numbers. I don't want to see all of them. I mean, if I maybe I do, and then I would just use this. But suppose I don't, I want to only plot, say, every 100 value. Okay. All right. So given now I've created this list called frequency where all these fractions are given, right? And I don't want all of them. I want every 100th one. So I want the 100th one, 200th one, 300th one up to 1,000. So I give the name frequency, and then in square brackets, SEQ for sequence, but meaning which ones of these do I want, right? I don't want all of them. The first one that I want, 100th, the last one that I want, 1,000, and in steps of 100. Okay. So this will give me the ones 100, 200, 300, 400 up till 1,000. I store all of them in data and then I print it. Okay. And I get that list. Okay, so now what's happening there, right? So after 100 tosses, I had 0.471. Then after 200, it was 0.475. After 300, it was 0.283. And it goes on by 1,000, it has come to 0.501. You can see again the settling down to 0.5. Okay. And people can play with this. They can try different numbers, different gaps, do it many times to see, whether the settling down always happens and whether there are any patterns to the settling down, how quickly does it happen. Okay. So this could be repeated. To get a fuller picture, you would repeat this many times, look at many plots of these and try to get a sense. All those pictures look very nice. Okay.
So
Okay.
in the output that you got there,
Hmm.
why is when you're doing print data, why is it giving you only 3 values?
No, 3, 4, 5, 6, 7.
वो
I
दोनों
mean,
मिला के
कुछ cut किया है उधर. I did because I wanted. I mean, there were more. Okay.
okay.
So I have cropped it, right?
1, 2, 3, 4,
Yeah, this is not
6,
all.
7.
There were also things away on the right. I cropped it, otherwise this would have become too small, right?
Yeah, but in mine, when I
It should
do
be
the
10.
I can see 7 values.
This goes
Oh,
to
7 and then Acha is giving it to me in the next line.
Yeah, multiple lines, right? So actually, what is the first? Those bracket 1 and bracket 8 are telling you how which output you are looking at. So if there are multiple outputs, it's saying the output is starting with the first one. Next row, the first guy is the 8th output. It's sort of keeping track of where are
7 in the
you
first,
if you are
8 in the
8 is the starting one.
right, right.
8, 9, 10.
ठीक है.
Okay. Okay, let's not spend too much time on this one. Don't try this because it's very similar. If I want to toss a die, I want to choose from the numbers 1 to 6. Right? So a sample, and then now instead of 0 to 1, I have 1 to 6. It will be choosing from 1, 2, 3, 4, 5, 6. Okay. And again, toss it a million times, store it in this thing called dice. Now there are other questions you can ask. How many results were less than equal 4, for example? Right? So that is by count. I mean, and if I want the fraction, then I use mean, right? Dice less than equal 4. How many entries of this dice were less than equal to 4? Right? You expect around 2/3, and sure it's 0.6672 for this one. Okay. count how many are between 3 and 5. This is to just tell you that you can combine requirements also. Okay. So what do I mean between 3 and 5? I mean greater than equal to 3 and less than equal to 5. So okay. So you run both the tests. You say which entries are both greater than equal to 3 and less than equal to 5. That gives you entries that are between 3 and 5, that are from 3, 4, 5. Okay, so this is for having two requirements. But sometimes you have, okay, I want this to happen or this to happen. I'm happy if I got 3, I'm happy if I got 5. So how many times did either 3 or 5 happen? Okay, so you instead of the and symbol, you have just this vertical line. This stands for or. So mean dice equal 5, dice equal 3 means dice equal 5 or dice equal 3. Okay. And if you are not equal 5, you run the test for equal and an exclamation mark for this means I did not want this to happen. Okay. So this means dice not equal to 5. So that's just to show that you can also combine different requests in different form. You can have union, intersection, complement taken care of by this notation. Okay. All right. Now let's look at this probability question. Okay. It's called the hat problem. Okay, there are 10 people. Everyone's wearing a hat. And somehow they're all different. The hats you can recognize later which was a hat and which wasn't. Okay. Now everybody throws their hat into some big box. Okay. And then after a while, I mean, you want your hat back, you go and pick a card. But you're not allowed to look, so you're picking one at random. Okay. The question is, how many people will be happy at the end of it? It's like how many people might get their own hat back.
Those are two different things. Those are two different things.
Yeah, could be. I'm assuming you were happy with your hat to begin with, and you're not a very competitive person. All right. Okay, and we are assuming every guy only picks one hat and doesn't know which one they're picking, so all are equally likely. All right. So the question is, what is the expectation? How many, right? How many people will get back their own hat out of these 10? On average, how many people would get it? Right? Each time it will be a different number. It's possible that nobody gets their own hat back. It's possible that everyone gets their own hat back. But on average, how many people will get their own hat back? What do you think? Suppose there were 100 people and we ran this experiment. How many you think would get their own hat back? You expect it to be a medium kind of number or a small number or less than half? How many think less than half? 50% is what you expect on average?
Less.
Less, how much less? 45? 40, 25, 20. Okay, so now of course you open a textbook, they will say create such and such random variable, assign probabilities, compute, and this is the answer. So that is boring, right? You want to, in a sense, you can do it. Nobody can question what you have done, but it doesn't really test whether you had any correct insight or not. Were you thinking the right way? Did you have some intuition that doesn't get tested when you just do that, right? So let's just run some experiments and see what happens. Let's get, okay, let's simulate 100 people tossing this hat, getting a hat back, and let's count how many got their own hat back. Okay. Yeah. Okay, don't read the whole thing. Just take it slow. It slightly spoils the fun if you read them. All right, first, suppose that there were 10 hat wearers. Let's start with 10. Okay. First, I just create the list of these people. Keep it simple. I just call them 1, 2, 3, 4, 10. Okay, now these are their names. 1, 2, 3 up to 10. And that goes into a list called owners. All right, now I want to actually shuffle the hats. Now I want to pick the hats one by one, right? I'm imagining like owner one has gone and picked the hat. Then so that will be one act of sampling from 1 to 10. But this time, once the hat is picked, it will not be put back. So now this is replace equals false. As it happens, replace equals false in R is the default option for samples. So I've not bothered to write this. So that's a good feature. If I were, I would have written it for clarity. Okay. So sample from 1 to 10 10 times, and because I have not put replace equal to, hats won't be put back. Once a hat is picked, it will not be sampled again. What will this do? This will create again the numbers 1 to 10, but in a jumbled order. Right? So for instance, look over there, the first output is 1 to 10, right? But the second is 1 to 10, but rearranged. That is coming from here. Okay. Okay. Now that's how you would do it. Now what I want to do is I want to count how many matches there were. Right? Okay. So what's happening here is I'm again sampling. Now this is a new sampling, not the old one. I sample so many times, and if you put two lists and put two equal to, you are just asking how many times do the corresponding numbers match. Okay. Whenever the two lists are divided, multiplied, or you check for equality, you are looking at corresponding numbers.
Can you call the sampling in the sixth line some name as well?
Yeah, I could have done that. But I did it that way because for some future use. Because I want to do this many times. Okay, so didn't want to fix it as well. Okay. All right, so for example, this is fixed, this is not. Every time I run this command, a different sampling will occur and I will see how many matches occur. So what I said the first time I did it, I actually got 0 matches. Okay. All right, now there's something nice in R. If you want to do something repeatedly, there's a command called replicate. You have something that you did, you want to do it again. You want to do it 10 times. You say replicate and the command and how many times you want to do it. So this thing that is doing what I want, I copy it and I say how many times I want to do it and I put replicate. So now this thing will be done. Okay, I think that. Now this thing okay. So now that tossing the hat and counting the number of matches is happening 15. And I have printed over there. I did it 15 times. Do you notice how low the number was each time out of 10? 0, 0, 2, 3, 1, 1, 0, 2, 1, 1, 1, 0, 3, 0, 1. I never got 4 matches, never got 5 matches, never got 6 matches. All right. Okay. Then, of course, I could be interested in what was the fraction of matches in this 15 times. Okay. And it's something low, right? It's pretty close to 1. You can do it lots and lots of time, right? And you can see what happens. Okay. So the thing to note is it's actually coming out very close to 1. On average, only 1% is getting the hack back when I do it with 10. Now we should, okay, what this because it was 10. So, okay, so if it's with 10, only 1% is getting the hack on average. Now the question is, suppose I did it with 100 people, and how much would you expect them would be happy? So out of 10, it was 1, so out of 100, it should be 10.
So मेरे पास 10 में से 2 बार
हाँ, एक बार करेंगे, 2 बार करेंगे तो कुछ भी हो सकता है ना, बहुत बार करेंगे then you see that. Right, here's the interesting thing. Here I've done it with 100 owners and funds. It's again very close to 1. Okay. So with 10 it was 1, with 100 it is still 1. Can you guess what will happen with 1000? No, now it's not there, okay? I can't put the 1000 data. But can you guess what will happen now? 1. Were any of us expecting this? No. And so then one has something to prove that however many people there are, when you do this, on average, 1% is going to be.
चाहे एक हो चाहे 10 हो 100 एक का सारी एक में मिल जाए
But sir,
Nice problem.
number
theoretical proof.
Yeah. It's very simple theoretical proof. But that is always,
expected delivery.
okay, you set up a random variable that counts and so basically what's happening is the more people there are, the less likely that a particular individual gets their own house. But then there are more people, so the two are somehow cancelling and just getting the same answer. Okay. How long is this workshop supposed to be?
Just you want.
At least.
All right. Yeah, I don't think there's too much more to say. Okay, there is maybe one more example I think is fun. Okay, now in probability you don't always want to pick with equal probability. There are certain distributions. I may be picking from 1 to 10, but I may want 1 to be less likely, 2 to be more likely, right? And we have various standard shapes according to which you may want to pick. So for instance, you have the binomial distribution. So I may want my random, things to happen according to binomial distribution or Poisson or normal or whatever there is. Okay. So R allows you to do all of that. It doesn't have to be equal probability. You can say pick according to such and such probability. And other things are also there. So for instance, look at the binomial distribution. You remember what that is, right? There is let me remind you. So your base experiment is that something happens and there is something you call success, something you call failure. And success has some probability p and failure has probability 1 minus p. And then you do this n times and you count how many successes. So there are two parameters, n and p.
Sir, it means minimum at least one person will get their hand.
No, on average 1%.
At least
नहीं, not at least. फिर zero तो आएगा. हो ही सकता है ना 1 को 2 की मिले, 2 को 3 की मिले, 3 को 4 की मिले, finally 10 को 1 की मिले.
and also order
So
पे भी
average
depend
there is
करेगा.
probability है for average.
Order पे depend नहीं करेगा. It means the first person will throw the cap and the last person will throw the
No,
cap.
but then
The last
as
person
long as you have named what those people are, the rest doesn't matter.
अगर last से उठाना शुरू कर
Or
देगा.
Is it like a probability belongs to 0 to 1? That is why this is coming.
Which one?
So,
पुराने में?
upping a high to
Hat में नहीं. It means तो ज़्यादा भी हो सकता है.
Is it
Because
possible
the
to
range of possible values was 0, 1, 2, until say 10. Suppose there were 10 people, right? possible nobody gets in at that, it's possible everybody gets in at that. So the range of possible values is 0, 1 to up till 10.
Random variable.
But the high values are very unlikely. And therefore, the average is close to 0. Probably the most
Random
one and
variable is 0 to 10.
1 and 0 और 10 के बीच में कहीं भी हो सकती थी, but 1 नहीं. So that's close to 0. Okay. Right, so first there are just some basic commands which you won't use, but I just wanted to show you. Suppose there was a trial that you were doing 100 times and the probability of success in each trial was 0.1. Then you could ask what's the probability of having success happen 15 times or 20 times. You could ask for different probabilities. That is what the binomial distribution is. So the command for that is d binom. It's the probability density. So d binom, okay. How many successes you want? How many trials you had? What was the probability of success in each trial? And you get some number between 0 and 1. I guess you get that 0.032. Okay. Or you may be interested in a range. You don't just want to know if I got exactly 15. I want to know if I got 15 or less. Okay. So for that cumulative kind of thing, the command is p binom. Okay. If you do 1 minus p binom, you will get the number that were more. Okay. And similarly, but forget all this. R binom is the one that I want to talk about because that's again simulation according to the binomial probability distribution. Okay. So if you do R binom 10, 100, 0.1, it means it's going to choose 10 times. Okay. We're going to run this experiment of 100 and 0. I mean, it's over there, right? So you do it 100 times and then some number of successes happen. So for instance, the first time I ran it, 10 successes happened. Then I ran it a second time, I ran it 10 times. So each time some number of successes happen and those are listed there. Okay, so that is simulating a binomial distribution. Okay. Thank you. There's the last. Almost.
And one problem is probability. Typically, these, I know that, setting up random variable according to a distribution is always a difficult thing to understand, right? For students. Even in R, that's becomes a problem because this becomes like a black box.
Yeah, I mean,
So is there something that
so like you
which
can replicate, one could have just physically
I know, so I'm saying,
done it.
so do you find it, and this is a pedagogy.
I don't know.
Not this thing.
I haven't tried. So
I don't know. Somebody has tried.
Yeah.
Janaki, maybe you will.
Is it possible for the finite number of possibility or infinite extremes?
no, finite. Finite is also. You can give different distribution and select it.
Like a binomial distribution, if we are going to
A binomial to finitely है वैसे. Binomial में तो finitely options होते हैं. अगर 10 नंबर किया है तो 10 तक ही जा सकते हैं. So binomial is anyway one of the finite examples.
that is normal distribution.
Poisson would be infinite.
What's Poisson?
So you can Poisson it does simulate, normal it simulates.
This is not for the infinite case. This is not valid.
Binomial is not, but for infinite case, whatever are those, there are commands for those separate.
But it is possible for
Yeah. Okay. It does it. Poisson there's a command. Normal is infinite. There's a command. उस तरह के restrictions.
same. So this is B norm, is it P?
That pattern. So I think Poisson is POIS. B Poisson.
So in that case, as per the 15 number of times, we need to write infinite times.
No. वो तो एक experiment में. See, Poisson is what is Poisson? Poisson is a random variable in one experiment have an infinite. But each time the actual output is finite. Right? It will be 100 or 1,000 or million. It's just that there's no restriction on how big it is. And that 15 is how many times you ran the Poisson experiment. So you see 15 different outputs. Okay, maybe it's complicated. I assume this slide will be shared. So, but it's just a story, and you can look into it, in peace later. So, in probability, I mean, it is a popular story that we talk. How did methodical probability begin? Because some gambling problems made their way to people like Pascal and Fermat. We are doing complicated bets, and our intuition is not leading us to win. So there's something wrong with our understanding of how these chance events work. Can you figure it out? Okay. All right. So this person, I have no idea how do you pronounce this name.
Surely it's a name.
Yeah, okay. He will speak it whenever. Okay. So his problem. Yes. Okay. All right. Somehow people were in the habit of betting on if you roll a dice 4 times, do you get at least, do you get one once or not? Okay. And then various complex combinations of this people would bet on. So this guy had some intuition that if we are rolling 2 dice and I want something which works like this, what it should be. And so this described what he felt his intuition was. Okay, but when he put it into practice, he ended up losing more than he expected. Okay, and so he wrote a letter saying, "Look, this is my intuition. This looks fairly straightforward, but then I'm losing money. So what's okay?" And then these Pascal and Pharma had some correspondence, and this is one of the things they sorted out. This particular description is from this website, which you should take a look at. Uh, but what we can do is, without really trying to solve, we can just run the two intuitions and see what happens. Okay, so there were two things we expected to match. One was, of course, if you throw how many you simulate how many sixes you get in fourth row, and you're asking, do I get at least one so that I win? Okay, and so what happens for that? And that was a winning thing. Like the probability, if I'm sampling it many times, I'm seeing I'm getting 0.5. Okay. The other was what he had expected would work out the same was that if you take a pair of dice and throw them 24 times and you ask for, how many pairs of sixes are there, he thought this would match because he was thinking linearly, scaling and thinking. But the at least part actually screws things up. Okay. So, and so we can, in the simulation, see what happened to the poor guy, right? I mean, this is not an explanation by theory, but we are saying, yes, this would have happened. The first strategy was winning 51% of the time, but the second one is winning only 49% of the time. So anyway, so things that are, so if you want to start understanding something by simulation, you can see what seems to be happening, right? That one is actually not matching with the other. Once you have seen that, you can start looking for explanations and do deeper analysis. Okay, I think that's all I want to say about probability and R. Uh, Let me show you some petty pictures. Okay. Uh, Now, it often happens in maths that you know there is some process and then you have to do it repeatedly. Right? So, for instance, I might take a large number and take its square root, take its square root again, take its square root again, and ask, okay, where am I going to end up? Where do you think I'll end up if I do that? Let's start with 1,000, take square root, take square root, take square root. Where will I be heading to? 1. Each time it's becoming smaller. Okay. What happens if I start with a number between 0 and 1 and I take square root?
One.
So if I have a small number, is it square root bigger than that number or smaller than that?
Bigger.
The square is smaller. That means the square root is bigger.
When I joined college, this was a question asked by physics seniors.
Yeah.
कि तुम maths के हो बताओ
Square
9
root
का
is
square root क्या है 3 तो फिर बोलते 0.9 का square root क्या है without thinking you say 0.3 जैसे क्या maths कर रहे हो
Right.
But he never made that mistake again. Bragging work. Okay, so anyway, that's a simple process. And in fact, there if you end up, as long as you don't start at zero, end up at small numbers become bigger, bigger numbers become smaller. Or I mean, in calculus class, or you would have done the Newton-Raphson, where you keep applying the same formula to try to come to an approximation of something. Right? So this idea is, so what's happening is there is some function and you apply it repeatedly to its own output and then again and again. Right? Okay. So you look at a particular example of that. Okay, so that's called an iteration. I start with some number z1. I have some function phi, I apply it to z1. The number I get, I call it z2. Then I apply phi to z2, I get z3, I apply phi to that. Okay. Okay. Now, what we are going to do is, that we are going to look at this, where the numbers are going to work in as complex numbers. Then you are doing things in the plane and the numbers are jumping around, and that is when you can have some interesting 2D patterns. You can do the same thing with real line, but then you have the points moving on the line and what picture can you get out of the line. But in a plane, you can get nice picture, right? So you work with complex. Okay. But think of the same thing. And just do a very simple kind of iteration. I will have a fixed constancy. I'll just square the number and add C to it. And I'll do this again and again and see what happens. Okay. All right. So that's the quadratic iteration. What could happen? Well, one thing that could happen is that the numbers might get bigger and bigger and sort of blow up. That's one possibility. Right? Or they may fail to blow up. They may sort of settle down somewhere, or at least they may just move within some restricted area and not just keep blowing up and getting bigger. Okay, so let's sort of look at these two possibilities. Okay, so orbit means you take a particular number and keep applying phi to it. So you get the sequence of positions, you fix a number and ask where is it going, right? After one step, two step, three steps, that path is your orbit. Okay. All right. So you can look at the points which don't, we just keep moving around in some restricted region that we're calling stay bounded throughout. Or which just blow up, that we're calling diverging to infinity. Okay. The points that stay bounded, we look at all those points, they form some subset. We call it the filled Julia set for this iteration. He was the fifth mathematician, one of the first who really studied these things. And the ones which blow up, their collection we call the basin of infinity. Okay. And between these two regions, there is some boundary, right? Demarcating one region from the other region. So that is just called Julia's. Okay, let's do a very simple example. Okay, let's just see. What do you think will happen if C is 0? My iteration is just Z going to Z squared. But in complex numbers.
Magnitude will be doubled and the angle will be
Right. Let's just think in terms of the magnitude. What happens to the magnitude? Because we just want to know is it blowing up or not. So let's forget the exact position and only worry about magnitude. So what happens to the magnitude if I just take Z going to Z squared?
if it is greater than equal then
It depends on whether the magnitude was more than 1 or less than 1 or equal to 1. If the magnitude is equal to 1, you are on the unit circle, and when you square it,
you skip
stay on the unit circle, right? Mod Z square will also be 1. So points on the unit circle will just keep moving around on the unit circle. So point, yeah, right? So that's in the boundary region. Points inside what will be?
like convert to 0.
Suppose mod is Z is less than 1. And every time you square it becomes smaller. So those will all go to 0. What happens if mod z is more than 1?
Closer.
Yeah, then it will start moving down. So here the Julia sets and so on are easy to see. Right? The filled Julia set is the unit circle and everything inside. Those are the things that are not blown up. The facing of infinity is everything outside the unit circle. Those are the things that are blowing up. The Julia set is the boundary, that is the boundary circle. Okay, now all I'm going to do is just show you, if I ask Mathematica, right? So Mathematica is good because it has built-in command for computing the Julia set of some intellects for that intellect. So we just go straight appeal to that. It's also possible to write your own detailed code of the orbits and what they do, but we won't do that. Okay. We just want to sort of see that this is something fun to play with. Okay. So that's what we agreed to would happen with Z square. Right? This is the filled Julia set. That's the basin of infinity, and that is the Julia set, the boundary between it.
This is when C is 0.
And when C is 0, phi z is just Z square. Okay, now I think this week I will skip your typing the mathematical code, but I'll just tell you what you have to do in future to do it. Okay. But let me also show you that if you now changed it a little bit, much more interesting things. Okay. So suppose I look at z square minus 1. And I ask for the filled Julia set inside picture on that.
Blank stuff.
Let's change z square to z square minus 1 made this huge difference. And at a much more interesting set. That's a fractal. Why is it called fractal? Because you can see that a certain shape is being repeated and becoming smaller. If you were to zoom in, you see that this process doesn't stop. Okay. The left is it's basically the different iteration, more complicated looking one leading to the same picture. This is just a small example that you really only need if I'm looking at quadratic, it could be z squared plus something times z plus some constant. You don't need to look at the general case. By completing squares, you can always reduce it by and through a shift, change it to the z square plus c. So naturally, that's the only thing we really need to do. Same shape, but in a slightly different location if you see the numbers on the horizontal axis. Okay. So by a change of coordinates, you can convert the left to the right. So you really only need to concentrate on z square plus c.
This is the real, is it?
No.
It could be common.
Yeah. Sure.
You're going to give us
Put no restriction. No, why do you? Okay. I'll just run you through. So there's a thing called Wolfram Cloud where you can run mathematical. If you type Wolfram Cloud, you will get taken to this website. Okay. Mathematics are expensive, but there's a free version you can use online. So you can go to this sign up for free and do it. Okay. So you'll have to give them your email and your password, and you will get a free account. Once you log in, you will see something like this. And you just need to click on your notebook to have a screen open up where you can do your work. Okay. So this is what it will look like at that stage. Now, this is the blank space where the commands can. So let me show you. Okay. So for instance, it's very simple. You just write Julia set plot, and you write, the function that you want to iterate. So z square minus 1. And you tell it what is the variable name you're using. So of course that is, and it will produce the plot. Okay. All right. Now a lot of work is going on internally. Okay, but forget that. And this picture you can copy and paste somewhere. You can expand, you can pull on the corner for a better look. Okay, that's what it looks like. You see the fractal aspect. No?
You can change the coloring.
Yeah, you can do all that. This is just the default stuff. There is something called color function you can use to change the coloring according to the patterns that you want. And here by putting color function none, I've got rid of the colors and only the boundary is now being shown. Okay. But generally trying to show only the boundary doesn't really pay off. The boundary is so complicated, it's actually easier to look at the 2D and not ask it to actually draw the path. All right, so for instance, the same thing. You could also uh, decide to plot only part of it. So you can say which coordinate range I want to look at. So here we're doing the same plot, but plot range and then minus 0.5 to 0.5 horizontally and 0 to 0.8 vertically. So now I'm just looking at a small part of the full picture. Right? And I can zoom into that and see what's yeah, not so fast. And I will. But here these are all worth seeing in turn. Now the thing is, different values of C give you different pictures. So the fun is in playing with different values of C and see what kind of pictures you end up with. Okay. All right. So in this first row, uh, here's what's happening. Julia said plot all this, and I'm trying these four different values of C, 0.1, 0.2, 0.3, 0.8, and I'm getting these four pictures. So when Z was 0.8, I had this blob, almost a circle, right? Remember that C equals 0 was a circle. C equal 0.1 is slightly away from us. C equal 0.2 more away, and now the bulging is happening in more interesting ways. Okay. 0.3, that solid region has collapsed, kind of exploded. It's not there anymore. Now there are scattered points, though they are still kind of in some pattern. Okay. And then by 0.8, it's totally scattered. Uh, that's all right. Of course, your C could be negative, and these are some examples. Okay, that's imaginary. No, that's negative, right? So I took minus 0.3 minus, again, the shapes are changing. And after that one, it would again sort of disintegrate. Okay. And C is complex, so it doesn't have to be real. Here I've taken imaginary ones. So with 0.6 I for C, I get this, and then here it's actually that's a nice picture. Let's blow up some of these.
This is an inbuilt coloring or you've given?
No, I've because then it looks. I didn't want the code to look complicated. So I just went for all the default thing, but you can play with the choice of colors. Yeah. Something look better in black and white actually, because then the patterns are clear.
It's cute like
That's nice, no?
Can you change the internet bits and colors?
No.
So nice. Can I see the first one zoomed in?
Yeah.
I mean, you can show this one.
No, I understand.
This doesn't go with the rest. Needs to be like
So even though otherwise it may look fairly smooth, but if you really look at this boundary, you see it's very jagged and lots of repetitive
the
patterns.
map of
Kashmir. And this one's also interesting because now it becomes like strands, broken up strands.
shows like a river bed. the psychological experiment, like the neurons.
This is where it's broken apart, but it's like strands. In fact, if you zoom in, there aren't any strands. Everything that looks like a strand, if you zoom in, you find it broken up. And you see some smaller strand there, you zoom in there, that's broken up also.
Oh,
Okay. All right. So in fact, we go back and show you. I mean, sorry. Yeah. Okay. All right. So there's a theorem uh, by one of the people who started all this. But the striking thing is they came up with this when these pictures were not available. They can physically see one thing in the example. Either there is one single sort of blob, or it's totally exploded. Right? There was no picture which had two blobs away from each other. That's actually a very striking theorem. That called the fundamental dichotomy, that the Phil-Julia set has only two choices, either connected, meaning there's one sort of blob, you can go from any part to any part, totally disconnected. You can't go from everything is separated by some space. Okay. So it's either like that, one single blob connected, or like this, totally blown out. So then, now as soon as this happens, there's a natural question, right? Which C produces this kind of behavior? And then you can group points into two types. The complex numbers which produce connected Julia sets, and the complex numbers which create the exploded ones. Okay. So there is this famous set called the Mandelbrot set, which consists of those C for which the Julia set is connected. That's what that set looks like. That's the Mandelbrot. Again, he started exploring it when these pictures were not available. That's one of the very impressive things about these pointers.
So looking at all those complex numbers,
Yeah, if you do the
Z square plus C,
quadri-
that
yeah,
is
you get
the
a connected.
connected Julia set, then the Julia set, and this is
The black one is those ones.
the black one. So, but he's not iterating it or anything. Right? It's not
No, I mean you iterate for each C. Is it connected? It's a part of the black set. It's not connected.
Yeah,
and
yeah,
the
yeah.
word
This
C
is just the
connected.
value of C.
C.
Those
not-
C's for which
that
the
is connected. But this is itself a fractal again.
that's the
Okay, now this is interesting. Some portions of it are easy to derive. Yes, just basic sort of fiddling with quadratic equation or something will do it. Like that line that you can derive, that first circle, you can easily derive that. Do you see that white shape? What is that called? Cardioid. It is the actual cardioid you come across in two variable calculus. Okay, exactly. That's it. It's not just something like it. It is exactly.
what is the
Last week, somebody asked me, some student, what is the importance of cardioid? Real world importance, I think it's the Mandelbrot. Okay, but again, okay, sorry. So I'm just almost ready to stop, but here also, Mathematica has a built-in Mandelbrot command. So just type Mandelbrot set plot and it will produce. And then you can zoom into different parts, and the boundary is the interesting side, right? So you can zoom into different parts. Yeah.
what happens if you use Q? Z Q?
I'll point you to some pictures. You'll have to do your own coding, I think.
Oh,
Okay.
why are you saying loss into this one?
Now here I'm just right, so you can tell it which portion to draw. You give the coordinates of this corner and that corner, and then it gives you that rectangle. So we zooming into the top part. That's quite fascinating because you see little copies of the Mandelbrot set appearing in different locations. Okay. I
So if
think
you go
we all
zoom in into that little black, it will look like.
and
Wow.
and one of this space between this sort of thing. These are interesting spaces to look in. There are other kind of patterns. Yeah.
So what is the orange color meant to?
No, it's just the outside stuff in this case.
But it's cotton, you said.
No, this is the black is the set.
Black is the
Then,
Mandelbrot set.
no,
Where he sort of argues that you can find fractal geometry in various natural phenomena and all. Okay, so lots of pictures and things. Slightly more modern, a bit more mathematical, fractals and chaos by Addison. Uh, Tunaki, Gita, I have this book, Learning Maths through Modeling and Simulation. So there actually you can find the mathematical code that produces all this. Here are some really nice articles on this and related things. Like this was quadratic iteration. You could ask the same thing for Newton reaction, any kind of iteration. That's actually another very rich source of factors is to see what happens with Newton reaction. Does it converge or does it not converge? Okay. All right. So these are various articles, talks about Newton's method. This talks a bit about history, Cayley's problem, Ray Newton's method, and Gilbert Strang's article also basically saying how to use all this in the classroom to interest students. And there's some fun websites where you can explore Julia sets and Mandelbrot sets, where you can really zoom in. With mathematical, I mean, also optimized for any of this, right? It's a more general purpose software. Certainly on the free version, there are restrictions and it becomes very slow. But if you write code which is special purpose to Mandelbrot set, things go faster and there are websites you can come up with. Right? So anyway, check in the morning. These websites all work. Okay. So John Whitehouse, David Heck, and this is a bunch of videos on the applications. Okay, let's talk. Sorry, last part. I didn't really do as a workshop, but I guess the slides will go out to you and you can then follow, try the code in Wolfram and see what happens and then change the parameters and see what other pictures you can.
Share this PPT in the group.
No, it should be there on the website. No? On the group, yeah. There's a,
yeah.
For that looks where you
no, that is a small group.
There is a
I
common
don't
group
know
for
if
all the
it's
parties.
Up on the MTs. All these will go up on the MTA website.
Yes, that empty website as well as in the group also will share. It is already shared. The link is already shared. YouTube.
like,
Yeah.
that's it for this.
Yeah.
Yeah, but the PPT itself you can.
Yeah.
Yes. You share the PPT with me and I will share in the group.
So since you're talking about this Mandelbrot sets and Mandelbrot doing these things before computers, right? There is a fairly important, it's a historical note, but I think it's important because it set back the Mandelbrot theorem actually by some time. Because he created these Mandelbrot sets and he was proving various things about it. And then he conjectured that these are all connected.
Uh,
But he felt that it was not true for all of them, because initially they drew this thing, and then in the first paper of Mandelbrot, if you see, they are not connected. So Mandelbrot was quite frustrated by that and his inability to set it up on true. And then somebody else, I know forgotten another person who's contributed in this, when it will come. So he was saying that no, it should be connected, and he was trying to prove it. Mandelbrot said, no, look at my paper. Then you know what the explanation was? The printer,
Oh,
the thing, he felt that it was this thing, it was not right. So he had actually disconnected, he made it into little islands. And Mandelbrot believed because he didn't draw it back, whatever he did.
yeah.
So he thought these guys were better at it. He gave it to them. So he saw it, and so he thought it was a counterexample, in fact,
Oh.
since other people did it and they recreated it and said, no, there are no islands. It is in fact connected. So they went back and republished it. And actually, Mandelbrot had the proof. But he was so discouraged by the fact that he couldn't generate the connected sites. That's because the people who were drawing it made this. So, and it's a problem because these things are really subtle. Really subtle. So today the tools make all the difference. So he talks about it in his part of the.
Anything?
Okay.
Anything they want to?
Yeah.
They want to say that we want to break 40, yeah?
Yeah.
Anything else?
So thanks for your patience. I mean, it was a
It was very tough time, but you enjoyed.
Let me make one announcement, please. So, thank you all for your active participation. And as we come to the end of our experiment in University Mathematics Workshop, we hope you have gained a valuable insight and a deeper appreciation from the practical applications in mathematical concepts. And there is a tea break, and the computer session, again, workshop 3, will be organized in the very same class. Yeah, you can. After half an hour.
So, tea will be same as in the morning. Same
Yeah,
place.
the reception area.
But they don't have place, so probably showing here. Next workshop is